So good evening to all. Is the audio and video clear for everyone? Right. So any questions with regard to the previous session to anyone? Say. Any queries or doubts? Right. So if not, I want to discuss about the module of today's session. So I want to discuss about two-phase method, which is similar to Big M method, what we are solving now for minimization problems. Later, I want to discuss about the degeneracy in the simplex method. And I hope that in the previous class, one of our students asked a doubt with regard to the basic solution, basic feasible solution, etc. So I want to discuss a sample problem on this, taking from the previous year question. Fine. That is the module of our today's session. Clear to everyone? Any queries so far? Right. So, as we know, we are applying the simplex algorithm for maximization case as well as minimization case. And we have discussed about dual concept also under the simplex method. The problem generally while solving the minimization is you have the inequalities of the type greater than or equal to, in which we are using two variables, surplus as well as artificial, for a single inequality. So that what happens while going with the computational task, it becomes tedious to compute the total table and eliminate the variables one after the other under the iteration process. So to avoid that, two-phase method is a modification of it. In general, we use this method for always minimization case. Whenever the objective function is of minimization case, there we use the two-phase method. For maximization also we can use, there is no difference at all. And the procedure is described by different authors in different ways. On the whole, we just do like this. For the original problem, we will write the objective function as well as constraints with the canonical form, introducing slack, artificial and surplus variables. In two-phase, we construct or we solve the problem in two phases, phase 1 and phase 2. In phase 1, in the objective function, what you have written, we take all the coefficients as 0, 0x1, 0x2, 0x3, and only the artificial variables as well as slack variables will come. And the coefficients for them is 1 or minus 1, depending upon the maximization case as well as the minimization case considered. So we will take like this. Because while constructing the simplex table under minimization case, we will have m is presented in the objective function. So what happens while calculating zj as well as cj minus zj in the table, you are getting the results in terms of m, like 8m minus 2, etc., etc. This is becoming a computational hazardousness for us. So to avoid this, we take the coefficient here as 1. So computation procedure will become easy. Now what happens? We apply the simplex method for this thing. So since optimality is reached, we went to the phase 2. So in phase 2, we replace the original coefficients from the actual objective function and apply the simplex method again. If optimality is not reached at phase 1, immediately we say that the given LP problem has no optimal solution, so we terminate our procedure. This is the whole idea. Okay? Is this clear for everyone? What we are doing actually in two-phase method? Any queries to anyone? Right? So let me take a problem on this so that we will have an understanding what the solution part. Can I erase this? Fine. So let me take the problem. Minimize Z 12x1 plus 18x2 plus 15x3 subject to the constraints 4x1 plus 8x2 plus 6x3 is greater than or equal to 64, 3x1 plus 6x2 plus 12x3 is greater than or equal to 96, and x1, x2, x3 are greater than or equal to 0. So please take a note of the problem. After noting, inform. Right. Now, if you write the standard form, so for the first one, you are going to introduce surplus as well as the artificial variable. So first inequality we will, sorry, we will write it as 4x1 plus 8x2 plus 6x3 minus s1 plus a1 equal to 64, and for the second 3x1 plus 6x2 plus 12x3 minus s2 plus a2 equal to 96, and objective function will come as 12x1 plus 18x2 plus 15x3 plus 0s1 plus 0s2 plus ma1 plus ma2. That is the actual objective function, right? Yes or no? It is minimum Z, the minimization of Z. Accepted to all? Now, we are entering phase 1. We don't want to disturb these inequalities which we have taken. In phase 1, we rewrite the objective function as minimum Z. If you put all the coefficients of x1, x2, x3 as 0, only these things will remain. And we are replacing this m with 1. So the objective function will come as a1 plus a2. That is the thing. Clear? So we are not disturbing the subjective conditions. We are just rewriting the objective function like this so that all these coefficients here are 0 for the decision variables x1, x2, x3. So based on this, we are constructing the simplex table. Clear or not? So can I go for the table now? the table calculation? Okay, I will erase this. So coming for the table, it will come like this: 0, 0, 0, 0, 0, 1, 1, x1, x2, x3, s1, s2, a1, a2, solution and ratio. These are CJ values. These are the basic and basic coefficients. And we are performing with respect to a1 and a2. The values come will as 4, 8, 6, -1, 0, 1, 0. And then 3, 6, 12, 0, -1, 0, 1. Solution is given by 64, 96. So for the time being, I don't want to compute Zj as well as Cj minus Zj values, which you can do on your own. Now you just tell me what are the key columns here to replace. I think you know what to do next. Now you can understand the difference between regular simplex table and this two-phase simplex table. Any questions for anyone in the construction of simplex table under two-phase method? Right. If you are clear, you simply calculate Zj as well as Cj minus Zj and tell me which column is to be replaced. First, second, third. Which one is to be replaced? Exactly. If everyone agree with that, then I go further. Because I don't want to compute these values, which is nothing but the waste of time in the class session, because you know how to calculate these values. Accepted, or you want to mention these things also on board? Right. Okay. So we are replacing third column. So we are going to find the key element here. Again, dividing with the solution with this, it was 64 by 6. And here 96 by 12, it is 8. Among these things, this one is the smaller. So I say this is the key element, the pivot element. Accepted? Right. Now we are leaving the corresponding variable. So x3, a2 will be replaced and coefficient of 0 will come here. So what we are doing in the next table, this is a1, the coefficient 1 remains as it is, a2 is replaced by x3 and the coefficient 0 will come. And then I am going to do the modification here. 12, we are going to divide the entire row with 12. So 3 by 12, 1 by 4, 1 by 2, 1, 0, minus 1 by 12, 0. Now see one understanding that since we are replacing a2, if you are interested, you can compute a2 column. Otherwise, you simply put blank here. There is no need to calculate a2, because as and when the artificial variable left under the iteration process, it will not come in the further iterations. So that is the advantage here. And this is 8. And you are going to perform the corresponding row operation here. If you require, I will notify the operation, or straight away I will fill the gaps. What you say? Right. So it is going to come as 5 by 2, 5, 0. Yeah, sorry. 5 by 2, 5, 0, minus 1, then 1 by 2, 1, dash, and at the end the solution will come as 16. accepted to all? It is minus 1 by 12. Let me write it clear. Fine. Now again we are going to calculate Zj as well as Cj minus Zj. Now you can understand the thing, since 0 is presented here, calculation of Zj as well as Cj minus Zj becomes very easy. That is the advantage of two-phase method over simplex method. Now you simply check, then tell me which column is to be replaced or selected as key column. So 1 into this, we are going to perform like that. X2, right? So this is X2, and to select the pivot element, the solution values are divided with this thing. So 16 by 5, the ratio, and 8 divided by 1 by 2, so 16. So obviously that value will be the minimum ratio, and we say that 5 is the pivot element. Accepted? Any doubts for anybody so far? Any confusion? Right. Now I am going to take the third table. So this is occurring for X2. So the artificial variable A1 is replaced by X2 and 1 is replaced by 0. So we are going to get it as X2, 0, X3, 0, and you are going to modify the rows. So if you allow me, I am going to fill the rows. Can I? Right. The thing is 1 by 2, 1. I will write, yes, 1 by 2, 1, 0, minus 1 by 5, 1 by 10, 16 by 5, and then 0, 0, 1, 1 by 10, minus 2 by 15, 32 by 5. These are the corresponding values. You can cross check that later. Now, if you calculate Zj and Cj minus Zj as well, you can check optimality is reached because all the values here has become 0. So, what is the testing condition for optimality under two-phase method is nothing but we are checking the regular condition that Cj minus Zj values all must be either less than or equal to 0 or greater than or equal to 0 as per the minimization as well as maximization case. And since this entry, the solution column entry gives the value of objective function, it must be 0 always. So if you substitute the values, it must be 0 because x2 takes the value 0, x3 takes the value 0. Here. So that optimality is reached. However, Cj minus Zj values must be less than or equal to 0. That is the criteria, or greater than or equal to 0. So once we achieve the optimality, now we are entering into the second phase. So one should ensure that since we are performing the iterations on artificial variable, right? So whenever artificial variables are removed under this process, then only we have attained the feasible solution or the optimal solution, whatever you say. We are going to enter the second stage of this two-phase method. If artificial variable is not removed, then we say that the system has infeasible solution and there is no solution at all. And one more thing is, sometimes I am going to take one more problem also. Artificial variable is presented here and objective function value is 0. In such case, after building the next stage, we are going to get the optimal solution. So there are two situations arise. In a brief manner, I am going to say that if artificial variables are eliminated, so we have the possibility to get optimum solution done. If artificial variables are not eliminated, one variable is presented there, so we are checking the objective function value, that is maximum z or minimum z. If its value is 0, then okay, we go for the second stage. If the value is less than 0, then we say that it has no solution. That is the overall idea. Fine? Or you want me to repeat? Clear? Or you want me to repeat the condition? Right. So now what is going to happen? Yeah, I will say again. To check the optimality under two-phase method, under phase 1, all the artificial variables must be removed. So while construction of these tables, all A1, A2, A3 must be removed and replaced by the variables x1, x2, x3. If it is done in the procedure, it means that you are going to get the optimal solution in the construction of second phase table, right? That is 1. If not, if there is one variable presented there, artificial variable, we will check the objective function value z by substituting the solution values in that. So what happens if the solution value is 0, the objective function value is 0, then you can go for the second phase. If the objective function value is not equal to 0, it is less than 0, then we terminate the procedure. There is no need to construct second phase table, and we say that the system has no solution. That is the conclusion. Accepted? Fine. So I am going to start the second phase table. Shall I? I want to erase this whole table. Thank you. Now the final table stage, it will come like this. So I am entering into the phase 2. Now understand that in phase 2, while writing the simplex table, I am avoiding the writing of the columns A1, A2, the artificial variable columns, because they are removed in the iteration process. So if at all one variable is presented, then only we mention that column. Otherwise, there is no need to mention that artificial variable column there. We simply stuck ourselves to the slack or surplus variables and the decision variables. And the original objective function values will be placed there. So 12, 15, 18, 0, 0. And what are the variables we are taking after replacement is done? X2, X3. The solution values will come as, I think it is, yeah, 18, 15. I think I need to write like that. Yeah, 18, 15. Is that fine? How I am building the simplex table? Now, what are the entries to be filled here? In the first phase, you have an optimal table. So those optimal table is exactly placed here without disturbing the entries. So I am taking them as it is. So 1 by 2, 1, 0, minus 1 by 5, 1 by 10, and then 0, 0, 1, 1 by 10, minus 2 by 15, and the solution comes as 16 by 5, 32 by 5. Now you can check that the same optimal table is considered here without any disturbance. Only the top objective coefficients are taken from the function and the corresponding coefficients and the solution. That's all. Now you can check for Zj as well as Cj minus Zj and check for the optimality. Fine. So if you calculate the values, it is going to come like this: 300 and then 21 by 10, 1 by 5. I left the part of Zj values calculation on your side. I simply calculated Cj minus Zj. Since we are doing minimization problem, our optimality condition is nothing but all the Cj minus Zj values must be greater than or equal to 0. Since it happened here, optimality is reached. The solution values which I have mentioned there are nothing but the regular solution values. So it takes that x1 equal to 0, x2 equal to 16 by 5, and x3 is equal to 32 by 5. And substituting these values in the objective function, you are going to get the value as 768 by 5, the minimum Z value. You could check on that. So this is the way in doing simplex method for the two-phase procedure. Any queries so far to anyone in the procedure application or something? If anybody has, you can ask. How we got final values? See here, this is the solution column, right? These solution values I am taken simply. This is for x2 and this is for x3. The previous table of phase 1 is taken exactly here without any disturbance. You can check that in phase 1, the same table you have constructed. The same values are obtained there. I am replacing the same value. For x1, see, under the iteration procedure, you have only x2, x3 are there. x1 is not there. So x1 is taken 0 by default. That is true. So let me take a simple thing. Since you know how to solve the matrix equations, let me say I have n unknowns and m equations. Generally, to find the solution part, we check the condition that m is equal to n or not, n is greater than m or not, or m is less than n. We will check like that, right? Yes or no? N variables, m equations in matrices at the school level or +2 level. So there we have found that if m is less than n, we have n minus m independent solutions are there. So that we will take a free variable. Can you recollect the definition of matrices? Ax equal to 0 as well as Ax equal to b we have solved. In the Ax equal to 0 system, or Ax equal to b also. Can you recollect that thought? So that free variable, we are fixing it as 0. So x1 is 0 here. Or there you are going to take that x1 is a constant, k. Fine. So you simply understand that if you have values for the two variables, it is okay. The third variable will be treated as 0. That's all. You just understand like that. What are the variables are presented here in the basic section? those solutions are there at the last column. So if there is a variable which do not have any value in this table, means you treat it as 0. Fine. Okay. Can I take one more problem on this thing? Okay. I want to do a little modification here. Procedure is same, there is no difference at all. In writing the objective function, I want to do a little change because some others also mentioned like that. Yeah, that's a good question. Always in the examination point of view, they will ask for using two-phase method solve the problem. So my intention is like this. Suppose a question is asked for LP problem under simplex method. Now what happens if I am a student, depending upon the question pattern, how I am going to use a method for solving the problem. The first thing is I will observe whether it is maximization or minimization, the objective function. Clear? If it is maximization, generally inequalities are given as less than or equal to. Straight away I go with the simplex method. If it is minimization, then what happens? Inequalities are of the type greater than or equal to. Of course, mixing inequalities are also there. Then I have the only chance, which is big M method. If not, I have one more option that I can find its dual. Because for a minimization problem, the dual is maximization. So I have less number of variables, I can solve it. If the question asked that by writing the dual you solve, it is okay. Otherwise, I can choose my own method as per the problem concerned. So I will write the dual. It converts into maximization. I can solve it easily. Right? So if I am more interested to apply the big M method, two-phase is convenient because for minimization problems, computation process will be easy for two-phase method. That is the strategy I am going to apply. Clear to everyone? If the question particularly asked that solve the problem using two-phase method only, we should solve it. Please understand, we can apply the two-phase method for maximization also, but the majority is given for minimization problems. That's the key. Now, how I am going to apply two-phase method for maximization problem, I am going to discuss now. I just want to take an example on this. Because the simplex algorithm yields good results whenever the objective function is of maximization type. So simplex algorithm is meant for majority of the cases maximization. If you are a computer programmer, the algorithm holds good for maximization. So some authors states that you convert the objective function, which is minimum, by multiplying with minus. So all the values in the objective function are multiplied with minus. So minimum z will become as minus maximum z. So you do the same procedure without disturbing anything. So for the final answer, you put minus, that is nothing but minimum. That's all. That is the idea. So if the question is given for minimization, you multiply all the constants in the objective function with minus. So it will become maximum z with minus. So you do the regular procedure without disturbing anything. Find the solution. For the final solution, you put minus because the solution will come in negative because you have changed the thing, right? Is it clear or you are getting a confusion? Please say. Right. So let me take a problem on this first. Just hold on a second. So this was the problem which I am going to take. Minimum z 15 by 2x1 minus 3x2 subject to the constraints 3x1 minus x2 minus x3 is greater than or equal to 3, x1 minus x2 plus x3 is greater than or equal to 2. Already non-negative restriction is there, right? This is the problem which is given to me. Now I am going to write the corresponding canonical form as well as the objective function. Now I am going to write 3x1 minus x2 minus x3 minus s1 plus a1 equal to 3, x1 minus x2 plus x3 minus s2 plus a2 equal to 2, and for the objective function I am writing it as maximum z minus 15 by 2 x1 minus plus 3x2 plus 0 s1 plus 0 s2 and minus a1 minus a2. Now see the difference, how I have written the objective function. If you write the regular canonical form, the objective function will look like minimum z 15 by 2 x1 minus 3x2 plus 0 s1 plus 0 s2 plus a1 plus a2. Accepted? This is the regular form of writing. Usually you write for the problem. Because for minimization, always plus a you should take, plus m will come. So, no need to change signs in constraints because I am converting the minimum problem into maximum. That's why I put minus. Please understand that while describing the big M method, I said whenever you introduce the artificial variable a in the objective function, we will write its coefficient as ma or minus ma depending upon the objective function. If it is minimization, we write plus ma. If it is maximization, we write minus ma. Can you recognize that point? That's why since we are taking m as 1, I will write like this. If you take m as 1, this is for minimization and this is for maximization. That is the way we usually write. Clear now? That's why I have written the two objective functions here. This is the actual objective function which is given and this is the canonical form which we write actually. And by multiplying with minus I have written like that. The constants also changed. Fine. Now I am applying the two-phase method here. I am going to construct phase 1. Shall I? Okay. And the question is, we are just changing the objective function only. We are not changing the signs in the constraints. Please understand that. We are not changing the signs in the constraints. And one more thing, whenever you have any inequality or greater than or equal type, we should understand that whatever the thing is there, on the RHS side, you should have always positive things. Let me say if I have inequality like x1 minus x2 is greater than or equal to minus 2. Now, we take this inequality as minus x1 plus x2 less than or equal to 2, and by putting like this only, we solve the problem. There is a non-negative restriction on the right hand side resources. Okay? In that way only we change the constraints. Otherwise, we take the constraint as they are. Now let us take the values x1 x2, x3, s1, s2, a1, a2. All these values are 0, minus 1, minus 1. I am performing the case with the artificial variables, minus 1, minus 1, and these are the values. And minus 1, 1, 1, 1, 0, you can check on that. Please check the constants what I have written. 3, minus 1, minus 1, minus 1, 0, 1, 0, and then 1, minus 1, 1. I think I have changed like that. Yes. 1, minus 1, 1, 0, minus 1, 0, 1. Now I am performing iterations on this. Zj as well as Cj minus Zj. Now you please tell me which column I need to replace here by calculating these values. So I think you have found the difference between the previous method and this method under two-phase criteria. The only thing is the minimization is taken as maximization. Earlier you have artificial variable coefficients as 1, 1. Here I have taken minus 1, minus 1. That is the only difference. Since the objective function is maximization, what is the optimality condition for Cj minus Zj? All the values must be less than or equal to 0. Exactly. So earlier we check for greater than or equal to 0 for optimality condition. Here we check for less than or equal to 0 for optimality condition. So it is evident from your argument that we are going to replace this thing, column x1. So I will say that pivot element is 3 by calculating the ratio with solution, 3 by 3 and 2 by 1. This is the ratio and this is the solution. Accepted to all? I think you are all well acquainted with the procedure so far concerned. That's why I'm skipping these steps to write on board as far as my understanding is concerned. If you are particular in writing these values, I go with that also. If anybody asks those steps also, I will write them if you are interested. Yes or no? I go with the majority decision. Right. Then just give me a second. So later, after this replacement is done, I am going to write the corresponding variable here. So a1 is replaced with x1 and 0 will come here. This is a2 with minus 1. I will straight away write the modified table. It will look like this. So 1, minus 1 by 3, minus 1 by 3, minus 1 by 3, 0, 1 by 3, 0. And you can avoid that thing also. 0, minus 2 by 3, 4 by 3, 1 by 3, minus 1, minus 1 by 3, 1. And the solution also you can calculate here. The solution will come as 1, 1. Could you check on that? If you're clear, I go with the next. So you simply calculate Zj as well as Cj minus Zj and give me which column is to be replaced then. Now, one advantage here is, since you are taking 0 here, you are avoiding computing with multiplication under ZJ procedure. You take only this thing. The thing which have largest coefficient, that column we are going to replace, isn't it? That is the advantage here. All of you agree? The technique under two-phase method, how it is convenient to calculate the procedure, right? So this is the key column. To select the pivot element, what happens? This solution is divided with the key column entries. So here 1 divided by -1/3 gives a negative result. So we avoid the ratio here. Whenever negative or undefined things comes, we avoid that. Again, if you divide with this thing, this is 3/4, the minimum ratio, this is the pivot element. So while taking the minimum ratio, we avoid negative and as well as undefined things. Clear to all? Say, if everyone is clear with this, then I go to the third iteration procedure, third table. Shall I? I will simply fill the values there. So A2 is replaced by X3. So X1 gets 0, X3 gets 0, and you are going to write the corresponding tabular values there. It is going to come like this: 1 minus 1/2, 0 minus 1/4, minus 1/4, 1/4, 1/4, and then 0 minus 1/2, 1, 1/4, minus 3/4, minus 1/4, 3/4, and the solution part will come as 0, 0. I think that the thing is going to come as 5/4 and 3/4 at the solution part. Sorry. Now you can check that optimality is reached here, and you can observe one thing: the two artificial variables are completely terminated in the iteration procedure. So if you take the exact table and substitute in the two phase, the second phase, I am going to say, take the regular objective constraints. So x1 takes the value 5/4, x2 takes the value 0 because it is not there, and x3 takes the value 3/4. You substitute in the objective function straight away, the objective function which I have modified, and give me the value. Say, I think my question is clear for everyone, because I am not going to construct the next table because you know what to do. So anybody has any queries for the construction of that second table? Whether optimality is achieved or not? Yes? Is that positive or negative? Please tell me that thing. Is it plus 75/8 or minus 75/8? Yes. So since I have written the objective function as maximization, the answer will come as minus 75/8. Since our thing is minimum, so we take that minus of minus 75/8, this is the minimum z. So for the solution, whatever it is, we put minus sign, that will be taken as the actual solution. In general, the answer will come in negatives. so that you will get the positive thing. Okay. Is it clear to all? Yes or no? Right. So I want to conclude the discussion over this problem, and I will take one more example where artificial variable is presented under two-phase method. But before that, I just want to start a discussion where it will change on the basic solution, feasible solution, etc., etc. Yes, in the previous problem also we could have done the same. Why not? That's why I have taken the two changes. One thing is I have kept the objective function as it is, minimum z. Artificial variables I have taken +1, +1. Some authors mentioned that you convert the objective function into maximization, take artificial variables -1, -1 and do the procedure. Whatever it is, the thing is same, the answer won't get changed. Because you are going to follow different type of textbooks, right? Some others may write in different manners. On the whole, the solution will not change. The decision variables will take the same values. Whether you put -1 or +1 by changing the or without changing the objective function. Okay. That's why I have taken the two methodologies, whatever they decide. Can I erase this thing then? So what is the question is to find minimum and then all the constraints are less than or equal to 0. I actually didn't get your logic. Can you elaborate, please? You are saying that all the subjective constraints are less than or equal to 0? The inequality is what we are taking actually? Yeah. That is just like the homogeneous system, right? X equal to 0 form. So how do we solve the homogeneous system? If you recollect the matrix row operations earlier, one variable is going to take independent. I will take such kind of problems also. Don't worry. And if you have a problem ready with you, you can give. We are going to discuss. So which sign is to consider for answer and how? Yeah. I think you get the solution values in the last column, right? Accepted. Right. So in this procedure, I have written that minus maximum z is equal to the objective function, because the original objective function is given as 15/2 x1 minus 3x2. I have modified this as minus 15/2 x1 plus 3x2. Accepted? So here I have substituted the same values there, 5/4 and 3/4, because in the table I have taken artificial variable coefficients as -1, -1, because I have changed the objective function. So the same objective function I am considering. Please understand, solution won't change, only objective function is changing here. So in this you substitute the values. x1 takes 5/4, x3 takes 3/4. If you substitute the value here, you are going to get minus 75/8. So for this answer I am taking minus, because original function is minimum z with 15/2 x1 minus 3x2. If you substitute 5/4 here, you will get the same thing, plus 75/8. Yes or no? That's it. Fine. So let me take one problem. Just hold on a second. That's a good one. Just hold on a second. I think you are saying that you have a inequality less than or equal to 0 or greater than or equal to 0 with the subjective constraints here. So that how to proceed with the solution is our question, right? As we have asked. I have an objective function. Some constraints are framed here. This is not your question. So you just post the problem, then we discuss. In the middle, I am going to start a new thing. Yes, you can post it in the group. No doubt. So just hold on a second. I just want to take one thing. The question is given that maximum z x1 plus 2x2 minus 3x3 plus 4x4 subject to the constraints x1 plus x2 plus 2x3 plus 3x4 equal to 12, x2 plus 2x3 plus x4 equal to 8, where x1, x2, x3, x4 are greater than or equal to 0. Fine. I think this is the previous year question given earlier in the year 2015. I hope so. One of the previous year questions. So the question asks that find all basic solutions which basic solutions are feasible which basic feasible solutions are degenerate non-degenerate basic feasible solutions and then optimal solutions. Without solving problem. So this was the question asked in the previous year papers. So without doing the simplest method, you are going to solve the problem like this. What are the basic solutions? Which basic solutions are feasible? Which basic feasible solutions are degenerate and which are non-degenerate? And without solving the problem, which basic solutions are the basic feasible solutions are optimal solutions? That was the question asked. Okay. I think some of you have found this problem earlier. I hope so. Are you with me? Is my voice clear for everyone, or are you getting any disturbance in the audio? Clear or not? Fine. So have you noted this problem? Now it contains 4 variables and 2 conditions or 2 constraints, let me say. So if we have such type of situation, how we are going to solve? The thing is, 4 unknowns, 2 conditions, so I can say 4 minus 2. 2 independent solutions. This thing you have learned at solving matrix problems. Yes or no? Can you recollect that thing while solving the matrices? Eigenvalues, eigenvectors, system of homogeneous, non-homogeneous equations at +2 or BTech level. Idea or no idea? Okay, if not, the thing I am going to do here is, in the constraints, I am going to set 2 variables as 0. I am solving the remaining 2. Fine. That is my outline idea. Shall I proceed? Okay. So what are the things I can do? I can put x1 equal to 0, x2 equal to 0, so that I am going to solve x3 and x4. I can put x1 equal to 0, x3 equal to 0, so I am going to find the values of x2, x4. Then I will do for that so what are the other combinations you are going to get? x1, x4 already happened. Can you find any other thing? Putting 2 variables 0 and finding the other 2. Right. x2, x3 setting as 0. And you are finding x1 and x4. I hope what I am doing is clear for everyone. Okay. Right. So after finding, you can find z also here. So if you put x1, x2 as 0, in the 2 constraints, the first equality will become 2x3 plus 3x4 is equal to 12, and then 2x3 plus x4 is equal to 8. Now solving these two, can you give the values of x3, x4? Now the procedure is clear for everyone. What I am going to do, right? x3 is equal to 3. And x4 is equal to 2. x4 is equal to 2, right? Three comma 2. So x3 is 3, x4 is 2. Our thing is, the variables are as non-negative restrictions. So these two are non-negative values, so you can compute z also. So what is the value of z? These two are 0. You are putting 3 here and putting 2 here. What is the value of z then? Substitute in the objective function. -1. Now, since we are going to find the profit must be always positive. You cannot consider this solution. Accepted? Fine. Let us go with other things. You put x1 equal to 0, x3 equal to 0. Then it comes x2 plus 3x4 is equal to 12. I put x1, x3. So x2 plus x4 is equal to 8. And you are going to solve them. You give me the values of x2 and x4 as well. 6, 2. That's right. Again, you put these values in the objective function. And you are going to get the value of z also. x2 is 6, x4 is 2. Answer is 20, right? Again, let us go with the third choice. So these two are completed. I'm going with the third one. x1 equal to 0, x4 equal to 0. It comes 2x, x2 plus 2x3 is equal to 12. And then x2 plus 2x3 is equal to 8. Am I correct? Yes. Now, these are dependent equations, right? So if you put one variable as 0, what will be the value of the other? If you put x2 equal to 0, what is the value of the other? It is also 0. They are dependent equations. Yes or no? The system gets unsolved. So you put a dash here. Fine. Now go with the fourth option. x3 equal to 0, x4 equal to 0, and you are solving the equations. So in this case, z will not be there. Two 8 or 4 8, which one is correct? Four 8, right? Again, we go with the thing. So if 48 is the answer, sorry, substitute the values in the objective function, give me the value, 20. So z is equal to 20 here. Then go with this option. x2, x4 are 0. You are going to find the respective answers. 4, 4, right? Then what will be the value there? -8. Fine. And then the last option. -12, 8. Are they correct? -12 and 8. Okay, x1, x3, if you put 0, x1, x4, our values are you getting solution for x1, x4 or not? Yes, give me the values of x1, x4. x1 and x4 values. Not possible as x4 must, of course, you just give me the value there. x1 is -12, that's good. And 8, right. And what will be the z value here? 20, right. Now what happens? Generally, while finding the basic solutions, feasible solutions, we do this procedure. depending upon the number of variables as well as constraints here. So what happens? A basic solution means a solution which satisfies the constraints as well as the non-negative restrictions also. If such is the case, now what happens? You are putting these values are 0, so they are called as non-basic. Since you are finding the values for them, these are the basic. So the solutions which you have found all are basic solutions here. x3 is equal to 3, x4 is equal to 2, x1 equal to 0, x2 equal to 0. These are the basic variables. This is a basic solution, right? Among which satisfies the non-negative restriction also, they are feasible. So here we won't consider this solution because x1 is minus 12, which won't satisfy that all the variables must be greater than or equal to 0. Accepted? Yes or no? Now, while solving these, at one position, these values are also become 0, isn't it? You have a dependent equation which is possible there. Accepted? Now, this solution, we call it as degenerate. If you go for the degenerate solution definition, if you have a basic solution in which one or more variables are 0, such solution is called degenerate solution. So these two are non-basic here. x2 and x3 are basic variables. While solving the basic variables, you get dependent equations. So you should say one variable must be equal to 0 or the two variables must be equal to 0. So such solution is called degenerate solution. Clear? Any questions? No? Right. Among which we won't consider this thing. It is negative. It is negative. And optimality is attained for two things, 20 and 20 here, the maximum z value. So these two are the optimal solutions. So we should write 0 there. So optimal solutions are attained by 2 points, x2 equal to 6, x4 equal to 2, remaining 2 are 0, and x1 equal to 4, x2 equal to 8, remaining 2 are 0, and the optimal value of z is 20. We won't consider the last value because x1 is negative, and z is equal to minus 1, we won't consider. So this is a basic solution, but it is not feasible because z is minus 1 there. Remaining are feasible solutions. This is also not feasible because z is minus 8, and this thing we won't consider. That is the overall idea for the problem. I hope you get the idea how to solve by writing all the solutions. Okay. Do you need any more clarity over this problem? In computing the values? So which are degenerative? x3, x2, x3 you didn't get here, right? These are degenerative. And you can say minus 8 thing also degenerate. Difference between feasible optimal means See, I have 4 variables. All the variables must be non-negative restrictions. So I will find the values of all the variables, right? So I will take the positive constraints. I mean, the solution where it is positive, all are feasible solutions. Optimal means if you check that I got z value 20, 20, 20. However, let me say z is equal to 12 for some time. So among which z is given by the maximum value where that is called the optimal solution, which is feasible, right? Variables values must be non-negative. Solution value should exist. Those are feasible, right? And this thing is degenerate case because solution values has become 0 there. And also, whenever you have -8 thing is there, that is also we can take it as degenerate because you are not getting the actual thing. Remaining are non-degenerative because we are getting a correct solution for us. Optimal means the thing which you have the maximum value for z, that is optimal. Okay. Fine. So similar kind of problem is also given earlier in the previous year papers. So if you're interested, just give me an idea for it. So feasible and degenerative are same in this problem. Feasible means z value should exist and solutions are non-negative. So you can assume like this for this problem. Let us have one more clarity. After doing this problem, we have a better idea. This is the problem given in 2003. x1 plus x2 plus x3 is equal to 3. 2x1 minus x2 plus 3x3 is equal to 4. Fine. Is that visible for you? So we would go with the same problem. It is asked in 2003 in the previous year question papers. Since we have 3 variables, here objective function is not given there. So you are simply computing the values, that's all. So what you are going to do, you put x1 equal to 0, determine x2 and x3. Similarly, you put x2 equal to 0, determine x2, x3, I mean x1, x3, and you put x3 equal to 0, determine x1 and x2. So the solutions which are non-negative, we are calling it as the basic solutions. Which satisfies z also, basic feasible. Which won't give z or degenerative. In a nutshell, we can say like that. If you are particular about that thing, I will give the definition as a copy in the group, so you can have the discussion. The definition part. How we are defining it. So could you give those values to me? x2, x3, x1, x3 and x1, x2 by setting those values as 0. So x2 5 by 4, x3 7 by 4, right? 5 comma minus 2, 7 by 3 and 2 by 3, right? So all of you agree with this? Two by three, 7/3, right? Fine. So we don't consider the things which have the negative thing. So remaining are the feasible solutions. If the objective function is there, you are going to substitute that. So the solution which gives the maximum value is called optimal. Remaining are only feasible solutions. Okay. So these are the two questions asked on these basic feasible solutions criteria in the previous year questions. Rest of all are given only on simplest method and other methods. So I'm going to wind up our today's session here. So we will meet on Monday on degeneracy in simplex table. The thing here is, whenever you are calculating the minimum ratio, so far the problems we have discussed, minimum ratio is not equal, it is distinct. So if minimum ratio is 0 or one of the variables are 0, how to proceed next? That is the concept for degeneracy in simplex table. Okay. So later, the concept of simplex in linear programming is completed. So we will go with the previous year question paper straight away. We are going to solve all the questions. I will post the link in group. You can take it as an assignment. So we can have a discussion in the group. So whatever the problems you are getting doubt, we are going to discuss in the class itself. So that we have command over all previous year questions asked on simplex method under linear programming as well as the graphical method also. Is that assignment suffice for everyone or you need more practice apart from the previous year questions? Say. Then from Tuesday onwards, I am going to start the transportation problem. I will say that this model will be very interesting for you, and these are very computational convenient and getting solutions, etc. So compared to simplex table, these are very convenient in getting the logic and solving the problems. That is my upcoming plan for the next week. So that's all for today. If you have other questions, you can ask. Any other queries, please? To anyone? This chapter will be completed by, if you are good enough to catch, it takes 1 week more. So by August 20th, 25th, you can say, it will be completed. Complete operations research, the linear programming part will be completed. Assignment problem, transportation problem, as well as simplex, all will be completed. Later, we are going to start with reanalysis because that is somewhat pending for some more students. I hope so. May I know which batch you have joined? Right. So by the time these two things must be completed for you, right? Linear programming as well as reanalysis. Is that right? Or these topics are already covered by you? Okay, fine. 13 July, right? So you were short of how many topics for the full coverage of syllabus? today itself, then it's interesting. So your tenure will be 1 year. So in the 1 year, the whole syllabus will be completed without any breaks. So only reanalysis. Then after this topic, we are going to start with reanalysis. I hope you can access the previous recorded videos also. If you're interested, you can watch that. So does this explanation suffice for you? I am taking reanalysis. Fine. If you have any other issues, you can ask to anyone. Fine. So shall we close our session now? Thank you. That's all for today.